So this is the general form for our exponential function, a times b to the x power. So anytime you have a base other than 1, and it can't be 0 either, where x is located up in the exponent position, that's called an exponential function. It could be exponential growth or it could be exponential decay. And the way you determine this back in Algebra 2 was you looked at the base. And these two problems, one of them's exponential growth and one of them's exponential decay. Do you remember which one's which? This one has a base of 2, which means this is going to be exponential growth. And the explanation that your math teacher was hoping for was that the base is a number greater than 1, and that's why it's exponential growth. However, if you look at the next example, you have a base of 1/2, which means it's exponential decay. And then sometimes kids would say things like, oh, the base is less than 1. It depends on how you define the base. The proper way to say it is that the base is between 0 and 1. So if you have a number between 0 and 1, you have an exponential decay. So if we think about what that means for our graph, remember exponential growth functions, and you don't have to sketch these down because I think there's a couple examples in your notes there on the next page. Actually, let me just flip. Yep, right there. So exponential growth functions are continually continually increasing from left to right. Their domain goes on forever. I don't know why I even attempted to draw that. That was bad. The range, however, has a range for this particular one that's not shifted at all. Its range goes from 0 to infinity, but notice, guys, there is a parenthesis on the 0 because 0 is going to be the asymptote, this horizontal asymptote right here. Oh gosh, can't draw straight. Which is at the line y equals 0. So you're not going to be able to hit a point on an asymptote. That's why they're using a parenthesis instead of a bracket. So the difference between exponential growth and decay is, besides the base, is that the shape is very different. So an exponential decay graph is going to be decreasing over its entire domain. We'll talk about y-intercepts and whatnot later. Domain is still negative infinity to infinity, and the range is still going to be 0 to infinity, however, because there is still a horizontal asymptote here at y equals 0. Now, there's a little note here about you must be able to graph this without a calculator, especially with this being our second go-around. Actually, if you want to be honest, guys, I think this might be the third time you've seen exponential growth and decay because you did this in Algebra 1 as well. We're going to have to be able to interpret things about the graphs, match up graphs, and know things about functions without actually having a graphing calculator. So this particular one, however, and this is why I gave you the chart, if for some reason you had to derive a really accurate graph for this one and you needed ordered pairs, you still could. Now, they already filled out the table for you. Thank you. And then here's what's going on, guys. You have 1/3 raised to the x power. So you choose the x's. They went with -3, -2, and so on and so on. So if you had 1/3 and you raised it to the -3rd power, exponent rules, guys, remind me, what happens when you have a negative exponent? Flips the fraction. So this is really 3 to the 3rd power, which is how they got a 27. So that's how they're getting 27, 9, 3, 1. And then here they have positive x's that they're plugging in. So 1/3 to the first, 1/3 to the second, 1/3 to the third. So it's not like you guys couldn't come up with these on your own. It's just obviously easier if you have a graphing calculator. So they graphed this one for you. We should have already known it was exponential decay before we started the problem because your base is between 0 and 1. And then when they plot it, we can see that it's definitely decaying. And they filled out all the information that you're going to have to fill out on your homework problems today. If time gets away from me, by the way, your homework assignment is the first bookwork that's on the page in the front of your packet. So we put the planner on the front of your packet this time. So it starts at page 166. There's a couple of 166 assignments, so make sure you do the right one. It's the 1, 5, 9, 13, 14. That's the assignment. There's more than that, but that's the assignment for tonight. All right, so if we had to graph without a calculator, it's not the end of the world. What you would do is you'd graph the parent function. So like this one, which is 2 to the x minus 1 power plus 1. Let's talk about transformations before we talk about the parent function. Well, I guess it doesn't hurt to write down the parent function. Guys, the parent function is 2 to the x power. So things that are not on the parent function are called transformations. So like x minus 1, how would that shift any graph if you had x minus 1? That would be right 1. That one, yes. And then when there's a +1 off to the side of the function, that's the k value, how would that shift a graph? That would be up 1. So if you did not have a graphing calculator, there's 2 ways you could approach this. You could make your own little table and combine that with what you know about the transformations and plot effectively. Or you could take the parent function and pretend like you're going to plot ordered pairs and move them using these 2 transformations. So like for instance, what if and this is referring to the parent function right now. What if I wanted to evaluate the parent function at 2, -1, 0, 1, and 2? Well, I plug -2 into here. I get 2 to the -2 power, which is flip the fraction and square it. So it's 1/4, or you could say it's 0.25. 2 to the -1st power, excuse me, is 0.5. Anything to the 0 power is 1. 2 to the 1st power is 2. And 2 to the 2nd power is 4. Now obviously there's other ordered pairs we can come up with because this has an infinite domain. But just for the sake of the shape, let's just plot these. But we're not really going to plot these, because after we plot these, we're going to shift them. Remember, everything's going to get shifted right 1 and up 1. So -2, 2.5 would be right about here, but we're going to shift everything right 1, up 1. So now it's located right there. And then -1.5 would have been right here, but everything got shifted right 1, up 1. And then 0, 1 would have been right here, but we're going to shift everything right 1, up 1. And then 1, 2 would have been right here, but everything got shifted right 1, up 1. And then 2, 4 would have been here, but everything got shifted right 1, up 1. So this is where Abruzzo ruins her picture because she has to graph. It's not as bad. So that is an exponential growth function, shifted right 1 unit and up 1 unit. A couple things to note though. The horizontal asymptote is no longer at the x-axis or at y = 0. Where is the horizontal asymptote located now? It's located up here at up 1. Or at y = 1, we would call that. Very good. So which part of the transformations moved the horizontal asymptote? Did the right shift move the asymptote, or did the up shift move the asymptote? The up one. Very good. So domain is not going to change for these because it's infinite, so -infinity to infinity. But the range no longer is going to start at 0. Now it's been shifted up 1, so the range is actually going to start at 1 and go to infinity. Because, and remember you're using a parenthesis on 1 because it's an asymptote. There's no x-intercept, but there is a y-intercept right here. Now if I graphed really, really well, which I actually didn't do half bad this time, I think I'd be able to tell that that was at the ordered pair 0, 1.5. But if you weren't sure if it was at 1.5 or not, because you graphed terrible like me, you would just plug in 0 into this function right here, the actual function. So 2 to the 0 minus 1 power, which is 2 to the -1, and then plus 1 is 1.5, yes. Okay, so we define the asymptote to be at the line y equals, oops, not 0, y equals 1. And then end behavior, we're going to go back to the traditional end behavior template, guys, the f of x thing. So f of x approaches something as x goes to the left, and f of x approaches something as x goes to the right. So I always do the left end behavior first. When I look at the left side of the exponential, it'll be this guy right here. What y value is the function approaching? It's getting closer and closer to 1. Very good. And then on the right side, which would be x goes to positive infinity, what y values are you approaching? Infinity. Very good. So back to that comfortable f of x behavior. That notation is going to show up a lot in math, so get used to it. And then the last question is this increasing or decreasing? You remember exponentials are not going to switch at any point. Is this one continually increasing or decreasing? Is this roller coaster up or roller coaster down? Roller coaster up. So it's increasing for the entire domain. Very good. So it's possible to do these without a calculator. Obviously not preferable. And when you guys are doing your homework, go ahead and use your table. I'm not going to fault you for that. However, you should be able to identify a lot of these components without using a calculator. Like if I just said what are the transformations, that should be just an inspection question. And remember, the SAT's coming up, and like half the test is no calculator. So there's some things you need to know without a calculator. This is one of them. All right. Can we talk about this? This is not on your paper anywhere. But 2 to the negative x power. Growth or decay? Okay, it's going to look like a decay when we graph it. Tell me why. You can give me the algebra 2 reason. Uh-oh, I heard the PreCalc reason over here. I heard reflection. I'm going to come back to you. Algebra 2 reason was this is really 2 to the negative first times x power. And what's the same thing as saying 2 to the negative first? That means 1/2, right? So this is the PreCalc, this is the algebra 2 explanation was the base is really a 1/2. 1/2 is between 0 and 1, therefore you have a decay. Nothing wrong with that explanation. But some wise soul, I don't even know who did it, said there's a reflection. Hey guys, think about what happens when you have a negative inside with the x on a function. Doesn't that reflect your function over the y-axis? It's a horizontal reflection. So think about this, guys. If you had, look at this picture right here. If you used to have an exponential decay, exponential growth, and you reflected it over the y-axis, you'd end up with an exponential decay. That's the PreCalc explanation as to why that's an exponential decay. So good call, whoever caught that. Thank you. And then this one always bothers kids. So I just want to bring it up in case it comes up in your homework. If there's a negative 3 in front of the function, it used to be a base of, well, it is a base of 2. So it's an exponential growth, and then the negative 3 in front is going to reflect it over the x-axis and vertically stretch it. So then there's a great debate. They're like, wait, is this exponential growth or decay? What do you think? It is technically still an exponential growth, but it's been reflected. So that's confusing. The reason is because of what's happening at the asymptote. An exponential decay has to do with as x approaches positive infinity, the function should be approaching a horizontal asymptote, and it doesn't happen in that example. So, all right, here's your very, very brief introduction to calculus, guys. There's a number called e. You've seen him in algebra 2. What in your brain pops up when you think about the number e? It's something to do with logarithms. Do you remember which logarithm? The natural logarithm. Thank you, PreCalc, for not calling that something silly. You know how many times I get in algebra 2, they call it in, or they call it line, or lin, and I'm like, what? And I get it. It's ln, so you're like, why is that natural logarithm? I blame the French. I think it's a French derivation from a French mathematician, and it was like logarithmic naturelle or something, and they went with ln as a symbol. Now, the reason why I'm very passionate about natural logarithm is this. Who knows my kids' names? Natalie and Logan, and we call them Nat and Log often. And one day, Mr. Abruzzo was signing a card, like for a birthday for some family member, and he wrote, like, when they're little, like, Nat and Log. And he looked up at me and he said, "You did not." And I said, "What? What did I do?" He goes, "You named your kid's natural logarithm." I said, "I did not." I don't think I did. Maybe, like, subconsciously. I don't know. I think he named the kids. I don't know what he's talking about. Anywho, this is called E is the natural number E. It occurs a lot in natural questions that we're going to be seeing in the future. So therefore, the natural logarithm and e are inverse. Well, the natural logarithm function is an inverse to the exponential base e function. So Euler, which is spelled like this, is credited for the derivation of the number e, which is approximately 2.718. Kind of like how pi is 3.14 approximately, e is approximately 2.718. You don't really have to understand how Euler came up with that. And I'm going to be honest, Euler probably didn't come up with it. Euler was probably the overarching mathematician in charge of all these little minions, and someone else came up with it, and Euler got all the credit. But whatever, I digress. So Euler supposedly did a little calculus question and found out when you take 1 plus 1 over n to the n power and you take it out to infinity, that's called a limit, you approach this magical number e. But he wasn't sure what to call it, so he decided to name it after himself because he's cool like that. Mathematicians. All right. So e, you don't have to understand why e is what it is, just it's a number, 2.718. So when I look at this question, this is e to the negative x power. So the parent function to that would have just been e to the x power. Now knowing what we just remembered about e is 2.718-ish. So if this parent function, would it have been a growth or decay if the base was just e and then it was to the x power? Would have been growth, because 2.718 is bigger than 1. So e looks something like this. However, what transformation was applied? A reflection across the y-axis. Very good. So I'm going to cheat. I don't really want to derive points with e because they're disgusting, and I would have to use a calculator regardless of my knowledge of e. So I know that it used to go through 0, 1, because if you plug in a 0 to any number's exponent, you're going to get a 1. And if you reflect 0, 1, you're still at 0, 1. And then I'm just going to fudge in a decay graph. Because it used to be growth, but then it was reflected across the y-axis, so it must be decay now. The domain is still negative infinity to infinity, because it is always infinite. Now the range, even though it's decay, is still 0 to infinity. Range measures from the lowest to the highest y value. So there is still this time it's a asymptote at y equals 0. I'll jot that down right there, y equals 0. The intercept is still at the ordered pair 0, 1. That doesn't change. The end behavior, however, now that it's been reflected, is going to be a little different than e to the x. So write out your end behavior template. All right. Now this time, when you look on the left side of your curve, where are your y values going? Up, up, up to infinity. And when you look on the right side of your curve, it's approaching the asymptote, which is 0 for a y value. Very good. And then is this function ever increasing or ever decreasing? It is ever decreasing from negative infinity to infinity. Very good. Okay. Feeling very familiar. I know some of those concepts were a little different. Went a little deeper than you did in Algebra 2. Let's take a look at worksheet 2A. And this directly correlates to what you guys see on the bright pink formula card you picked up. These are all formulas which are supposed to be review for you. However, I will say your textbook takes a more calculus approach to the formulas. So it's giving you the calculus versions of all these formulas. And you don't have to write these down unless you want to. And you can even change them on your card if you'd like. Just remember that that's not the card you get to use when you're testing. So this kind of resembles something you guys saw in Algebra 2, but in Algebra 2 it probably looked like this. Y equals a times 1 plus r to the t power. Remember seeing that guy? That's the generic exponential growth and decay question. Now if it's growth, you're going to do 1 plus the rate, but if it's decay, you have to subtract the rate. So in regular Algebra 2 we put a little plus or minus symbol here, and you guys had to determine whether it was plus or minus. I'm not sure what Honors Algebra 2 did for you. This guy is the continual exponential growth or continual exponential decay question. This is the calc version of it. This is the version you guys saw last year. We called it PERT because it spells PERT because we're clever like that. And then P is the original amount. They use the number E as your base and then raised to the R times T power. And then this big formula everyone hates, but it's not really that bad, guys. It's got an added factor of a compounding value. So this is used a lot when they do bank questions where you leave your money in a savings account and it collects interest quarterly. Well, because it collects interest more than once every year, they have to, notice what it's doing in the formula, guys. It's dividing your interest rate by that number, and then it's also multiplying the number of years you leave your money by that number. Because, talk to me about what's going on, guys. So let's say you put your birthday money in a bank account and it collects interest every quarter. First of all, how many times a year is it collecting interest if it's quarterly? 4 times a year. 4 times a year. And then, does it get all your interest 4 times a year? That'd be cool, but that's not how money works. So the formula calculates how much interest you will have, and it subdivides it into quarters. And it gives you a little bit in, you know, whatever that month would be, March. And then it gives you a little bit more later, and then it gives you a little bit more. Well, why is that better than just getting a lump sum of interest in December? Why is it better to get a little bit of money, a little bit of money, a little bit of money, a little bit of money? Because you're going to build money off of the extra money you have. And the formula accommodates for that. Now, when we do these baby Algebra 2 questions today, they're a little stupid because most people don't just let your money sit in a bank account. And if it's in something like a stock or a bond, things change. So these are very basic and simplified questions that we gave to you in Algebra 2 so you could understand the formulas. What we're going to do in PreCalc starting on Friday, or maybe not Friday, starting Tuesday, is we're going to look at more financial applications that are more real life, and we're going to be using some apps on our calculator. So look forward to that. All right. Formulas, formulas, formulas. Let's look at some problems. Biology. So a researcher estimates that the initial population of a colony of cells is 100. So for our formula, they call it n sub naught. So this is the n sub naught, the initial population. And then it's reproducing at a rate of 25% per week. So that is your R, and because they're reproducing, that means they're adding to the population. So it's adding 25%, which you'll have to write as a 0.25. And then they want to know how many cells are in the colony after 6 weeks. Now I will warn you, in PreCalc, you got to watch your labels. So here, they're measuring per week, and then they give you an amount of weeks, so they match up. We're going to have a question coming up where they don't match up, and you got to be careful. So this is T. All right, so here we go. The initial amount was 100. And then you're growing 25%, so that's 0.25. And then that's sitting around, not making any changes other than growing for, whoops, 6 weeks. That's a 6. So in your home screen of your calculator, could you please type that? And we're counting number of cells, so let's say that's a countable number, and let's round to the nearest whole cell, please. It even says about in the answer. You get 381? Okay, I want everyone typing that. Make sure you know how to type that in your calculator. 6 is up in the exponent, so make sure you're using the caret key. Okay. Financial things. All right. So we're going to invest $1,000, and it's going to collect 5% continuously. So that was your clue to use the formula for PERT. So the $1,000 is the initial amount that you invest. They call it P in this formula principle. The R is 5%, but how do you write that? 0.05, thank you. And then that's per year. And it's going to sit in the bank account for 10 years, so that's your time. All right, so here we go. In the home screen of our calculator, we are typing 1,000 times PERT uses the natural number E as your base. Who knows how to find E on their calculator? There's 2 places. If you use second natural log, I like that one because it automatically brings up an exponent for you. But the other place is right above the division key. If you use that, that is just the number E, so you'll have to insert your own exponent. But E to the, now if you're on a newer calculator, you don't need parentheses here, but if you're on an older one, you're going to need to group the power in parentheses. What are we at? 5%. So 0.05 times 10 years. So newer calculators, you don't have half of this stuff written down because your calculator has the right notation. Now guys, this is money. So an appropriate place to round money would be to the nearest cent. So give me to the hundreds place, please. Is it 1648 something? Okay. 1648 and 72 cents. All right. Make sure you're practicing the typing part. All right, so now same money, or no, not same money, different money. Oh man, I didn't do this right first hour. I wasn't listening to myself. It says we're supposed to compare. So we're going to do this problem twice. The first time is we're going to compound continuously, and then the second time we do the problem, we're going to compound quarterly. So continuously is PERT. So we have 5,000 times E, and then it's 8.5%, so make sure you're writing that appropriately. That's 0.085 times 10 years. And again, it's money, so give me to the nearest cent, please. And 23 cents, thank you. So that was collecting money continuously, which means literally like every moment of every day you're collecting money. Now we're going to compare it to quarterly. So for the quarterly formula, that would be the P times 1 plus R over N to the NT power. So that's 5,000 is the principal. 1 plus our rate of 0.085 divided by N, which is quarterly. What does quarterly mean? 4, good, 4 times. So N represents how many times you collect interest every year. So quarterly means 4 times a year. And then up in the exponent here, if you have a newer calculator, you don't need to use parentheses here, but you do have 4 times 10. Or you could just write 40 if you prefer that. You get 11,594.52. There we go. So logically, it shouldn't surprise you that you get more money when you collect continuously versus 4 times a year, because the rule is if you want to collect more money, then you should collect more money more times a year. So if you're comparing apples to apples on 2 bank savings accounts, if one collects more frequently but they have the same interest rate, go with the one that collects more frequently if there's nothing else different. But we all know this is not how banks work. They don't give you 8.5%. And they surely don't give you continual interest. So, these problems are a little lame now that we become older and realize that these problems don't really make sense. But that's okay. They're easy to get right on a test. So, all right, number 2 here, energy. In 2007, it's estimated that the United States used 101,000 quadrillion thermal units. I don't know what number quadrillion is, but it's got a lot of zeros in it. Someone Googled it first hour, and she said it had 5 sets of triple zeros. So it was like 1, and then 0, 0, 0, 5 sets of them. It's a lot of zeros. So we're just going to call quadrillion part of the label, because I'm not going to type that. And then it increases at a rate of, oh, careful, 0.5%. So how do you write 0.5% into our formula here? 0.005, teeny tiny. This is more like a bank account question. That's pretty much what you get on your savings accounts. Now be careful here, guys. This compounding formula, if this number right here is a 1, does it change the R? Does it change the T? No. So you really don't need to use the compounding formula. You can just use the regular old growth and decay formula. So you started out with 101,000, and you're increasing at 0.005. Now T, let's talk about how much time has elapsed. 13 years, very good. And it does say annually, which means per year. So it's to the 13th power. $765 after that? Okay. So 107,765. Remember the label though is quadrillion thermal units. So I think that's a lot. I don't know. Oh, and then everybody's favorite question. Rabbits. Rabbits are left unchecked. You remember this question when you were in middle school? And it was trying to talk to you about like sequencing? No, they don't teach. See, usually they throw this at middle schoolers because they think it's funny because they're talking about rabbits and like what rabbits do when rabbits are left to do what rabbits do, which is make more rabbits, by the way. Anywho, it gets out of control really fast. So these particular rabbits increase their population 10% every month. Yeah. So over the last year, they left these rabbits alone and they let them do their thing. And they started with 10 rabbits and they want to know how many rabbits are there now. Well, I don't know. Let's do the math. All right, guys, so this is a growth and decay question. Obviously growth, because rabbits are reproducing at a rate higher than what they were at. So 10 rabbits is what you're starting with, but you're increasing 10%. Now, this is where I need you to be careful, guys. They increase 10% each month, and they let 1 year go by. So how much time has elapsed? 12 months. Very good. So you got to watch your labels here. So this is to the 12th power. Please round to the nearest whole bunny. Think it comes out to about 31 rabbits? All right. All right, good. Oh, we're on good time. Let's keep going, 2B. All right. So this town is actually decreasing its population every year, and it's declining at a rate of 6%. So just remember when we're in our formula, since it's declining, it's going to be negative 0.06. So if we started with 12,426, predict the population 5 years later and 10 years later. So we're going to do 2 problems for each of these setups. So first, for annual declining, we're going to start with 12,426. And annual means you just use the regular growth and decay formula, but we are decreasing at 6%. And then for 5 years, we're going to figure this out. And remember, this is people, so you should be rounding to the nearest whole person. And you're going to figure it out for 10 years as well. Let's see. I think I got 9,119 for here. And then 6,693. Now let's do totally different math because we're going to use a different set of scenario here. We're going to be declining continuously. So continuously means you use the PERT formula. Whoops. P times E to the RT power. So let's think about this, guys. We started with 12,426. You're going to multiply it by E. Now your rate is declining at 6%. So how do you write that up here? Because I can't just say 0.06, that's going to grow. What if we did negative 0.06? There we go. And then you're supposed to multiply it by how many years you're going to let go by. So this first time it's times 5 years. And again, you might need to put parentheses here if you're on an older calculator. And then second problem you're going to do is the same thing except for it's 10 years. All right, so I got 9205 for the first one. And 6820. Okay. Fun stuff. Again, these problems are simplified as just an exposure for you guys. This is, no one sits around town going, I wonder what would happen if our population were to exponentially decay at a faster rate. Because, like, you don't control that. I hope. All right, number 5. Oh, you know what? We're going to save number 5 for tomorrow. All right, I'm going to stop the lesson there, because that takes more time than I wanted to spend. I do have photocopies of bookwork available to you. If that's going to increase bookwork production, if it's just the act of finding your book. So on the table back there behind our friends, there's some packets of the next few pages of bookwork, and there's quite a few coming up here, like bookwork, like the next 4 days, I think. All right. Cancel.